Perfect. Okay, well, thank you very much for being here. Thank you for the invitation to talk. This is joint work with Davide Pigoli, who was a postdoc also here at Stats Lab, and now he's a lecturer in King's College London, and John Aston, whom most of you know, who's a professor of statistics here, and now is the chief scientific advisor at the Home Office. So essentially, he's a spy now. Okay, so this is the talk about analysis of multidimensional functional data. So functional data is the analysis of data that has some kind of smoothness. You can think of curves where each curve is a data point, or surfaces. These are spectrograms, so these are the local time Fourier transforms of sound waves, okay, and this has smoothness both in the frequencies and in the time. And this is, you can think of this as a function on the cortical surface or on the whole brain, and this has some kind of smoothness. Every image has some kind of smoothness because, or in a different way, there is no fixed finite dimensional representation of an image or of a curve, because if you give me a discretization, I can always give you a finer one. This kind of data are called functional data, and usually when you model this kind of data, you assume that your data comes as IID realizations of a random function x that is typically in L2, so the space of square integral functions here on the unit Q, and this space is a Hilbert space, so more generally you can assume that your data is the realization of a random element in a Hilbert space. Now you have some realizations of this random function x, and typically what you're interested in the first steps of the analysis is the first order structure, the mean function. So you have x at t, you can take the mean of this and you take it for every t and you get a mean function. And the first order structure is interesting. The second order structure is also interesting, and that's the covariance. So the covariance between any two time points t and s is c of ts, and you can do this for every t and s. So this gives you a function that has based on two parameters that are on the unit q. What is really interesting, more interesting than just this function here, it's the operator it induces on the space of L2 square integrable functions. Namely, you take f, a square integrable function, and you integrate it against c of ts. This gives you a new function of t. So think of this as a continuous version of the matrix multiplication. Now, if there's something that you want to remember from this talk, is that when you're dealing with functional data, the real important thing is this covariance operator. And why is that? It's because the functional data is infinite dimensional, and you need to do some finite dimensional representation of it to be able to do anything, essentially. So the fundamental result is called the Calhoun-Love expansion. So it says the following: suppose that x is a random element of a Hilbert space, has finite square norm, expected square norm, and let C be its covariance operator, and you write C in its eigendecomposition. So it's the sum of eigenvalues times eigenfunctions times their transpose. Okay, so if you don't like this, just think about a singular value decomposition for a symmetric matrix. Okay, and what the Calhoun-Love expansion tells you is that if you center x around its mean, then you can write x in the basis given by the eigenfunctions of its covariance, and now you expand this and you get that x minus mu is a sum of scores times functions. So the scores are random and they are uncorrelated. The functions are deterministic and they are orthogonal. Okay. And this sum has the following property. If you're looking at the sum that minimizes the squared distance with respect to x, any sum, finite rank sum that minimizes the distance with respect to x, the optimal such sum is the truncation of this term here. And now the expansion, the approximation error, mean square, is given by the sum of the tail of the eigenvalues of the covariance.
So you're already using Mercer's theorem, right, to write that C in that SVD like that?
You don't need continuity to write it. Mercer's theorem tells you that you have convergence in the soup, but you don't need convergence in the soup to write this and to have this result. So yeah. So essentially what this is saying is that the covariance is really crucial, and you don't know the covariance in practice, but fortunately enough, if you compute the sample covariance, you have nice properties for it. So what you know that the sample covariance converges almost surely to the true covariance, and in a quite strong sense in the trace norm. So in infinite dimensions, all the norms are not equivalent, and the trace norm is one of the strictest norm. And you have also the following, you have also the rate of convergence for the estimation of the covariance given by the central limit theorem that tells you that if you center the sample covariance around the true covariance and you rescale it, then this is asymptotically Gaussian with the following covariance. Okay. So now, as a byproduct by perturbation theory, you can also get that the eigenstructure of the covariance is consistently estimated, and you can also have central limit theorems for it. So this is quite nice, but in our setup, you have a couple of issues. The first issue is the computational complexity. So I'm talking about this is a talk, this is work that has already been published, so it's a bit old, but it's the only thing I had that is related to scalability. So if you have a random function in L2 on the square, and you represent this x as in a tensor basis, so you have, for the first dimension, you have p basis functions, in the second you have q basis functions, okay. So m equals p times q basis functions, and now the covariance is of the order of m squared dimension. Okay. So computing or storing the covariance can be a problem. The second thing is typically what you have is you have hundreds of observations. So you have hundreds of observations, but if you have p equals q plus 100, then you have on the order of 10 million parameters, degrees of freedom. So even if you can compute the sample covariance, you're really worried that it's actually a really bad estimate. Okay. And this is just to illustrate the computational complexity. So here I have P, where I'm saying that, welcome, bless you. Welcome. You're saying that X, so it's a function on the square, and I'm saying that for each direction, I have p basis functions. So I have m equals p squared basis functions, and this is p here. And here on the y-axis, you have the memory used. And this line tells you how much memory you're using for a given p. So typically, if you have a slice of the brain functional MRI, this is going to be about here, so I think it's going to be around 100 megabytes of memory. If you have a full fMRI, then you have about 16 gigabytes of memory needed to store the covariance in memory. Okay, and this is typically the limit that you have now on laptops. Now, if you look at a full structural MRI, then the amount of memory you need is really high, and it's higher than a typical hard drive. And also the time required to compute this is really high. Typically the maximum dimension for which you can compute in a reasonable time is here. Okay. So what this talk is about, so you have this problem. What can you do? You can assume that the covariance has some kind of structure in order to reduce the computational complexity and increase the statistical accuracy. Okay. And so when people talk about structure in regression, people think about some kind of sparsity by forcing the entries of the beta, the coefficient vector, to be 0. Here sparsity does not make really sense, because if you force sparsity on the covariance, it's not necessarily going to still be positive definite. Something else that makes sense is assuming that the covariance is separable. And what does separability mean? If you have a function, random function x that is, imagine it's a spatial temporal process. So the first variable is a spatial variable and the second one is a temporal variable. Now the full covariance is what? It's the covariance between x at points s and t with x at points s prime, t prime. So that's a function of 4 variables. And you say that the covariance is separable if this function of 4 variables can be written as a product of a function covariance that depends only on the space variables times covariance that depends only on the time variables. So if you have separability, what you have? Well, estimating your covariance is much faster because suddenly you have much less degrees of freedom and it's more accurate. And now, if C is separable, the eigenfunctions of C are given by the product of the eigenfunctions of C1 times the eigenfunctions of C2. Okay. Now, if separability does not hold, this basis given by this product of marginal eigenfunctions is still going to be a basis. So it's still valid for doing some projections, but it's not going to be the optimal basis. So essentially what this is doing is you're assuming that C is separable, even if it's not. Well, it's giving you a biased estimate of the covariance, but it has lower variance.
I guess I could probably imagine that C2 could be stationary as well sometimes.
Yeah. So here I'm not assuming any kind of additional structure on C1 and C2, but you can add further things. So you can say that C1, for instance, is parametric and then C2 is stationary.
When you say it's still a basis, is it for a lower dimensional space or for the full dimensional space? It's just not the right eigenvalues.
So
eigenvectors.
It is a basis for the full space. If you really take the, so you want to take eigenfunctions that are in the range and add also the eigenfunctions that are in the kernel. So before we were here, and when you assume separability, then you're on this line here. Okay. So suddenly, even looking at data that is structural MRI, you can compute and store the covariance in memory if you're assuming separability. So just to give you an illustration, imagine that the xi's are 10 by 10 matrices. Okay, so this is each of these images is a realization. Okay. If you're looking at the covariance of these images, typically it has 5,000 degrees of freedom. And now if you assume that the covariance is separable, this reduces to 110. So it really decreases dramatically the number of degrees of freedom. Okay. Good. So what I've said so far is that the eigenstructure of the covariance is really crucial in functional data. It is not computable in some cases, but what you can do is you can assume that the covariance is separable, and that can happen. Okay. Now this talk is not about just how great separability is, it's about once you assume that separability is an assumption, can you test whether this assumption holds or does not hold? Okay. So if this was a talk about sparsity, my question would be, can you test if beta is really sparse or not sparse? Now, I want to have a test for computing this testing separability without having to compute the full sample covariance and without having parametric assumptions on the covariance. Okay, so I used to give this talk at places other than Cambridge, and then I would put this to explain, to just show how Cambridge is nice, and also to give a visual break before going into the maths. Okay, so in order to devise such a test, I need to introduce a little bit of mathematics. And the mathematics that is really important here is the tensor product of Hilbert spaces. So let me just remind you, a Hilbert space is a linear space with an inner product and a norm, which is complete under that norm. Now, if I look at this space of square integrable function indexed by space parameter and time parameter, what I can write is that this space is equal to the tensor product between the space of square integrable functions that are spatially indexed times square integrable functions on the time index. Okay, and what this really means is that if I have x of st here, I can write it as a sum, possibly infinite, of functions here times functions here. Okay. So it's kind of, we take all the products of functions here, here, we take their linear span, and now we complete it. Now, if I have H1 that is a Hilbert space and H2 is a Hilbert space, this space composed of all these products, sum of products, I call it H1 tensor H2. Now, if X is a random element of this tensor product of Hilbert spaces, and X has a finite squared norm, expected square norm, so by this I denote the norm of X, then the covariance of X is trace class. And what does trace class mean? Well, remember that the covariance is symmetric and it's positive definite, it has eigenvalues. Trace class means that the sum of its eigenvalues is finite. You're in infinite dimensions, so it's not given. It's not automatic. Okay. And I write C belongs to this to the set of trace class operators on H1 tensor H2. Okay. So now I want to introduce what separability means. Separability means the following thing. Suppose I have an operator C1 on H1 and C2 on H2, each of them being trace class. Now I can create a new operator on H1 tensor H2 by doing the following thing. I take U tensor V, U belonging in H1 and V belonging in H2, and I apply this new operator on it in the only natural way that is possible, by applying C1 on U, C2 on V, and now taking the tensor product between them. Now you complete by linearity and you get a new operator. And you say that an operator C on H1 tensor H2 is separable if you can write it as a tensor product, or here this is usually called also Kronecker product, as you can write it as a Kronecker product of C1 and C2, C1 being on H1 and C2 being on H2. Okay. So really this is the same thing as a Kronecker product, but in infinite dimensions. Okay. So now I have separability, and I forgot to say, separability of the covariance is a little bit like saying that there is independence. The covariance is the product of the marginals somehow. So now I've defined separability. How can I get a separable approximation for a given covariance? Because what I will do if I have a separable approximation, then I can take the difference between the two and I can look at the limits. Good. So to introduce this, I need to introduce a concept called partial trace. Okay. So what is a partial trace? It's a mapping that goes from the operators on H1 tensor H2 to the operators of H2. it does the following thing. If I have an operator on this space here that is of the following form, A1 tensor chronometric product A2, it maps it to the trace of A1 times A2. So this is indeed an operator on H2. And now the space of all these operators, if I close it linearly, is dense in this space, so I can expand it by continuity. And this partial trace, what is it? Well, if you look at matrices, if I have a matrix C that is indexed by I, J, I prime, J prime, okay, where the index I and I prime are from 1 to P and J to J prime are from 1 to Q, then what is the trace? So what is a partial trace of C? That's an operator on Rp. So it's indexed by I and I prime. And how do you get it? You take C, I, J, I prime, J, and here that's the same thing. And now you sum over J. So you fix the indexes I and I prime, and then you take the trace of the resulting matrix. If you look at it in the continuous version, well, it's almost the same thing. Take C of STS T prime and you integrate over S. It's really a trace on one of the dimensions, fixing the other one.
I don't know if I'm inclined to flip the indices 1 and 2 here. It's like TL1 is like a marginal distribution on the second space.
Yeah, so this is just terminology. So
I know.
the way I thought about it is that I'm tracing out one dimension.
Yeah.
So I'm tracing out dimension 1.
I know. I guess I would normally, if you think of marginalization, right, you would.
You would write pi
use
1
it the
for
other
the,
way around.
yeah. I think I thought more about this at some point, but anyway. Yeah. So think of it as exactly not you're thinking about it. Yeah, it's the opposite of what you're thinking. Great, okay. So now I have a nice characterization of separability. An operator C is separable if and only if I can write it in the following way. C up to a constant is equal to the product of its partial traces. So you have this, now you can write, if trace of C is different than 0, you can write that C is equal to trace 2 of C times trace 1 of C divided by trace of C. So by this formula, I define a separable approximation of any covariance. Now, something that you have to notice is that this separable approximation of the covariance is not linear, but it is continuous. So now I have everything I want, because I have the sample covariance, I have the separable approximation of the sample covariance. If I'm under the null that the true covariance is separable, then what do I have? These things converge. This converges to C, this converges also to C, so this quantity, if I rescale it properly, should converge to a limiting distribution. The problem is, if I look at this dn, it requires the computation of the sample covariance, which I didn't want to do in the first place. Okay. So how do you get around this computational complexity? You can project this dn onto the eigenfunctions obtained from the separable approximation. And this is written in the following way. You have dn, which is this difference rescaled. You project it onto the eigenfunctions ur, vs, ur, vs. And now this term, I call it Tn Rs. Think of it as the projection onto directions R and S, R being in the first space, S being in the second space. And you have a nice form for it, which shows that it's easily computable. Okay. And essentially what this is doing, it's on the left here, you're projecting every centered data onto this should be RMS, onto the eigenfunctions VR tensor US, taking the square of this. So you're estimating the product of the eigenvalues corresponding to this eigenfunction and this one, and this is one way of estimating it. Another way of estimating it is by taking the partial covariances and now looking at the eigenvalues. So essentially, it's a little bit like a chi-square test of independence. Good. So I have this general test, and now I have the projections. And under some assumptions on the random function x, I can have that this dn converges in distribution to a random element that is Gaussian. What are the assumptions here is I need a basis of the Hilbert space such that when I'm taking the inner product of x against this basis and I'm taking the fourth moment of this, these are summable. So if x is Gaussian, this is the same thing as asking that the eigenvalues of the covariance of x are root summable. So essentially it's asking that x is smooth enough. So Dn is asymptotically Gaussian. It's a random element of the space of trace class operators are H1 tensor H2. And because the separable approximation of Cn is not linear in Cn, it has a very nasty covariance.
Can you just go back one slide?
Yeah.
How did I think of that assumption compared with the expectation of the fourth moment of the norm of x being finite?
Sorry, say that again?
How should I compare that assumption that you have there with saying the expectation of the fourth power of the norm of x is finite?
So this is stronger, and essentially you need this because you need a central limit theorem for the sample covariance to hold with respect to the topology of the trace class, space of trace class operators. So usually you have a central limit theorem in kind of the Hilbert-Smith norm, the Frobenius norm, if you assume that x, the finite, the fourth moment of x exists. But here you need a stronger convergence because you're talking about traces.
Is it implied by any power of the norm of x?
I don't think so. No.
But it certainly implies that fourth.
Yes.
Fourth moment.
Yeah.
Does it imply that higher than fourth moments are finite?
I don't know. So in case x is Gaussian, yeah, I didn't think about this. Yeah. Right. Essentially, this is telling you that you have some preferred directions along which the fourth moment decreases fast enough. Yeah. Other questions? Okay, good. So you have this nasty covariance, asymptotic covariance, and if you look at the projections, okay, so you remember TNRS is the projection of DN onto directions RS. If I take a finite number of these projections and I look at the matrix of all these projections, this is asymptotically normal with a covariance sigma whose entries are given by this nasty expression, which involves fourth moments of x projected onto different directions. Okay. So this is a bit nasty, but if you assume that x is Gaussian, then suddenly you get a much nicer form. If x is Gaussian, you have the asymptotic covariance between Rs and R prime S prime is a product of two terms which essentially depend on the eigenvalues of the of the marginal covariances, their trace, their Hilbert-Smith norm or Frobenius norm, and this covariance, if you take r equals to r prime, you see that you have an extra term here, so it's kind of inflated along diagonals. So now you can estimate consistently this quantity here by just plugging in the estimators of each of these quantities in it, and using that you can get an asymptotic chi-square test for the separability under Gaussian assumptions. So this is what I'm going to do, and I'm going to present some other tests that you can do, and I'm going to compare them. So remember, you have dn, that is this difference between the sample covariance and the separable approximation being rescaled, and tn rs is a projection of dn onto direction rs. Now, given a set of indices I can take this projection, take the squares and sum them. And this thing, I know I can compute its asymptotic distribution, but I can also bootstrap its distribution. And since you're talking about bootstrap, you might wonder, why did I do all the asymptotics? The reason I'm doing this asymptotics is that we know that if you're bootstrapping something, you're going to get better results if you divide your quantity you're bootstrapping by its standard deviation, or you make it Peeblesy. Okay. So I'm going to look at these following tests also. So this is just a sum of the squared projections. This is when I'm taking the projections and I'm renormalizing them such that the covariance is an identity, and then I take the squared norm of this vector. And this is the test where I take each of these projections squared and I divide it by its marginal variance. So if I didn't know of the asymptotics, I could use this test and bootstrap the distribution. If I just knew the marginal distribution of these projections, I could use this test. And if I know all the distribution, the joint distribution of the projections, I can use this test. And I'm going to compare these three tests and see what the differences are. And something that you might think of is that, okay, I'm doing projections, and maybe the separability holds along these projections, but not in other directions. So one thing to look at is to take this difference here and you compute a norm of it, and you look at a test based on this norm. Okay. Now, this is going to be computationally more intensive, but potentially it's going to detect separability, departures from separability better than the projections. So just to summarize what I'm going to show in the numerical experiments, you have these three tests, and think of it as no studentization, partial studentization, and joint studentization, and this is now the norm of dn. And the asymptotic distribution, I know for this test, I know its asymptotic distribution, I know its chi-squared. And to sample, to approximate the distribution of these tests, I can use either a parametric bootstrap if I assume the distribution of the data generating process, or an empirical bootstrap if I don't know the distribution of the data. Okay. So in the plots, the plus arrow will mean that I'm looking at the asymptotic distribution at the p-values obtained under the central limit theorem for this guy. All the circles will denote parametric bootstraps, and all the triangles will denote empirical bootstraps. Continuous lines will denote the simple test. The dashed lines will denote the marginally studentized test, and the dashed dotted line will denote the full studentized test. And to compute the p-values for separability, I have an R package called covsep, and you can download it from CRAN. Okay, so these are some of the results. What I'm doing is I'm projecting all the time on the first eigen direction. Okay. And I'm looking at 4 different sample sizes. N equals 10, so that's really low. 25, 50, and 100. And as I go from gamma equals 0 to 0.1, I'm looking at the null hypothesis and then departures from the null that are higher and higher.
So what was gamma?
So gamma, I didn't introduce it, it's a parameter that tells you how separable you are. 0 is completely separable, and if it increases, it's getting less and less separable, the covariance. So I highlighted 3 of the tests. One is this one, which is based on the central limit theorem. Okay. And for sample sizes n equals 10 and 25, you're not respecting the level of the test. But as your sample size grows higher, you're respecting the level of the test, and you also have increasing power as the departure from separability increases. The other things you have, this one is the empirical bootstrap version of the fully studentized test, and this is the parametric bootstrap version of the fully studentized test. The nice thing you see is that even for n equals 10, the parametric bootstrap respects the level and has some power. And if you look at these circle with line results, this is if you don't use the asymptotics, if you don't studentize. This is what this is telling you is that if you didn't go through the trouble of computing the asymptotics and creating a studentized test, then bootstrapping will not respect the level. So it's a nice example of motivating the use of asymptotics. So that was under the Gaussian setting. This is the result under a non-Gaussian scenario. I've simulated data with a multivariate t-distribution. And the thing that you see is that the parametric bootstrap is here. It's the fully studentized version, and it does not respect the level. And this should be expected because I'm doing parametric bootstrap under Gaussian assumptions. The empirical bootstrap respects the level even for very small sample sizes. Okay.
Can you go one back?
Yeah.
Okay, 1 second. Do you think it's kind of strange that for n equal to 10, the non-parametric bootstrap is doing nicely in the non-Gaussian setting, not so good in the Gaussian setting?
Yeah, I don't know why.
But I mean, maybe this is just because, I don't know, it may just be an empirical thing. It's not that huge a difference.
Yeah, I think I used at least 100 replicates or more. Yeah,
How many bootstrap replicates and how many for this?
1,000.
And for this one?
So bootstrap replicates for getting the distribution is 1,000.
Yeah.
And then I think simulation replicates, it was also 1,000 or something like this.
But sometimes that's not enough.
Okay.
So it could be that if you, because this is different, obviously different settings. So the general idea, they will be comparable, but maybe the Gaussian and non-Gaussian is not comparable.
Yeah. Yeah.
I mean, what you can do easily is just run it with 2 different seeds and then see, each, and then see with 3, 4 different seeds and then see how much those vary, and then you have a kind of idea how much.
Yeah.
But it's also quite a straightforward calculation. If you've got a binomial 1,000, 0.05 random variable, then you know.
Yeah. So I didn't do a central limit theorem kind of comparison to see if they're really different or not.
Problem is you cannot go, as high as you like, because you always have, if you go to 10,000 bootstrap replicates and 10,000 of these, and
No, I was thinking if you're just looking at the number of repetitions of the whole simulation that you're doing.
Yeah, but you have to think twice, because the bootstrap thing is already an approximation of the quantile you're interested in.
That's true.
So, and actually, from my experience, it's more important to get more bootstrap samples than more pyramidal things, but okay.
So here, one thing that I want to emphasize is that I'm using this corresponds to the studentized version of the test under Gaussian assumptions. Okay, and so this is not the correct studentized version of the test under non-Gaussian assumptions, but it's still helping. It reduces the level to the correct level, even if it's misspecified in some sense. You see that the central limit theorem test does not respect the level. So, yeah, that's it. Now, if you increase the number of projections, so now I'm projecting into the first four eigendirections. Okay. What you see is that the central limit theorem takes a bit longer to kick in, but you have a very nice thing is that, first of all, the two bootstrap versions of the fully studentized test, they respect the level, and their power really increases dramatically compared to the non-studentized versions. So this is telling you two things. One is studentization helps you respect the level. The second thing, it gives you much more power than non-studentized versions. So yeah, so this is really nice. Here, even if you increase the sample size, these powers from the non-studentized tests, they don't increase, whereas the studentized version suddenly it explodes and it has perfect power. Okay, so one thing that is difficult with this kind of test is that you need to choose a number of projections onto which you project your full test. And what this slide is showing you is this plot here. Every entry of the plot corresponds to the power or the size of the test when projecting onto all these principal components. So think of it in the following way. If I take I and j here, then for each of these boxes here, I could have projections. So I have Dn projected on UR, UIVS, UIVJ. Okay. And what I'm doing is I'm taking the test combining all of these for I smaller than I bar, j smaller than j bar. And this test, I would plot its value at the coordinate I bar, j bar here. So here that's a test based on just one projection, and here that's the test based on all the projections. And what you have on the left is you're looking at the level of the test, the empirical level, and you're seeing that whatever the projection you take, you're always going to respect the level of the test. On the right, what you're looking at is a small departure from separability, and you're looking at this, the power of the test, and it's telling you that if you take just one projection or a few projections, you don't have much power. But if you take enough projections, suddenly you have perfect, you have 100% power. But if you take too many projections, then you get less and less power. Okay. And why is that? It's because you're kind of, if you're in the beginning here, you're capturing part of the signal. Here in the middle, you're capturing all the signal. And you're here when you're in the tail, you're actually capturing signal plus noise, and the noise becomes increasing as you go here, so you're missing the signal inside the noise. So that was for numerical experiments, and now an application to linguistics. So the data we have are are log spectrograms for 23 speakers indexed by K from 4 different Romance languages indexed by L, and each of them are pronouncing 10 different words indexed by I, and these are the numbers from 1 to 10. And what we do is we look within one language, and for the same word, I look at the residual spectrogram. So I take the average of all the spectrograms for this language and this word. I remove this effect from each of the spectrograms, and now I have R, L, I, K, K going from 1 to Ni, and these are replicates. I assume these are replicates of a process that depends only on the language. Okay. So the resolution of the spectrogram is that you have 81 points in frequency, 100 points in time, so the full covariance is has about 10 to the 6, so that's 1 million degrees of freedom. And your sample size here is 23. So you forget about estimating your full covariance. And what I'm looking at here, I'm trying to test the hypothesis that the covariance between of the process R for language L is separable. And I'm going to look at testing the separability using 3 kinds of projections. One is a projection onto just the first principal directions. 2 is the projection onto the first 4 principal directions. And 3 is a projection onto, I think, 20 principal directions. And what you see is that for French, if you're projecting onto the first 4 principal directions, you don't detect separability, but if you go to more principal directions, you detect separability. Italian, you detect separability right away for the first projection. If you go to the second, to more projections, you don't detect it, and more projection, you detect it. So looking overall, all of these languages have a non-separable covariance. And the reason for that is that if you look at how someone speaks, the word you're saying at that point, and it means in T, it has some frequency energy, and because you move only continuously in your mouth, you cannot say any, there is some temporal and frequency dependence closely in time. How can I explain this? What you're saying right now affects what you can say in in T plus delta T. And so covariance and time are not independent, and this is what this is telling you. But for the analysis, you can use such a separability assumption and do your analysis. What you have to remember is that all the results you get, you have to somehow temper them by the fact that your covariance is not truly separable. So you might be missing something in the data. Okay, so to conclude, what I've shown today is how can you test a structural assumptions like separability without having any parametric assumptions, but you can only do this when you have replicates. The nice thing is that if you know the asymptotics of your test, then you can construct tests that have better performance under the bootstrap replicates, meaning that you respect the level better and you have more power. The setup I've given you, it's a general setup in a Hilbert space. So if you have spatial temporal data on square or on Earth, it's going to be applicable. All the tests are implemented in a package called CovSet. And what I've shown you is only for tensor product of 2 Hilbert spaces. If you're thinking about fMRI data or MRI data. This is three-dimensional. Okay. So you could also create a test for three-dimensional separability like this, but then the covariance might get quite ugly than what it is already. So if you want to do it, have fun. Thank you very much.
So I guess a rather obvious question is what can you say about the asymptotics under the alternative? Can you, I mean, a fixed or local alternatives, can you get something depending on this parameter gamma?
So I didn't look into this. Some Holger, Deta, and Amitabh actually have a paper on testing for separability using a different kind of test, and they have shown that under the alternative you get perfect power using their test. Asymptotically, yeah. In our case, it really depends on if you capture in your projection the direction of departure from separability.
So it wouldn't be consistent. Right?
So if your angle between your projection and the departure from separability is different than pi over 2, then I think you have perfect power asymptotically.
But can you guarantee that? You can't guarantee that's going to be the case, right? Or is it just a matter of choosing enough directions?
So it's a matter of choosing enough direction. I cannot, it really depends on the alternative. So for a fixed alternative, I can tell you these projections will give you perfect power. But you cannot have, I don't think you can have a result saying that for any alternative fixed, then this projection is going to work. So your optimal projection somehow depends on the alternative.
That's okay, but you're trying many projections in the course of your test, right? So the question is whether by choosing sufficiently many, you can always guarantee whatever the fixed alternative is, that you will asymptotically have.
Yeah. I don't know. So it's the tricky thing is that
uniformly over a class of alternatives. Whose true departure from the null is sufficiently big.
Yeah. The tricky thing is that if you're really looking in the Hilbert space setup, you have an infinite number of projections. So just taking all of them and aggregating them in some way
you
will not
could
work.
always have something that's orthogonal to all of your projections.
Well, not always, because they span the space.
But you're only choosing finitely many projections.
Yeah. So essentially, in some sense, for quite a big set of alternatives, if you fix your projection and look at all the alternatives where you don't have perfect power, then this set can be quite big.
So when you're standardizing, you're using the asymptotic standard error. And yet, so I mean, it's interesting that it's the asymptotic one that's giving you the correction. Do you have a sense of what the actual one is?
No.
So basically the asymptotics just give you the form, and a form that tends to be effective.
Yes, yeah. The actual
So
one,
it's interesting.
I didn't compute the actual one, but yeah. Yeah. And essentially, ideally, we'd use this. This is the asymptotic covariance under the general setup.
Not separability.
No. So that's under non-Gaussianity. Yeah.
Okay.
So I'm using the asymptotics under Gaussianity to synthesize. Yeah. Other questions?